basically a direct translation of this find and fix. We're going to use automated techniques to localize the bugs, and then use patches to fix these bugs. For the localization, we build on work that Mukherjee actually presented in 2019 in Athens on spectrum-based fault localization in grammars. But we improved this substantially. We're now looking not at rules, but at individual rule positions. This substantially decreases the number of possible repair locations and gives us the efficiency that we need. Second, what kind of repairs do we use? We rely on small-scale operations that apply the standard string edit operations to the rules of the grammar. So we replace, delete, insert, or swap symbols on the right-hand side of a grammar. We deliberately use only small-scale patches to keep the search space long. If the bug requires multiple patches, we rely on our control to reapply more patches on similar or on the same location. And third, we check whether a patch is actually promising. We can check preconditions and post-conditions on the location to see whether the patch can actually improve the quality of the grammar. And we'll be looking at that in a lot of detail. Right, so this is the high-level view. We look at the grammar. We use automated spectrum-based fault localization to identify possible fault locations in the rules. We apply small-scale transformations on these rules to patch up the grammar, and we reduce the search space by using specific, explicitly formulated pre- and post conditions on the validity of these patches. So let's look at some examples. So the idea is that grammar patches can be implemented via symbol string edit operations. We just apply the standard operations at the designated position of the items that our localizer spat out as potentially suspicious. All right? Here's an example. There's the rule on the left-hand side with the bullet designating the position. So we found out that the symbol name in that rule may be wrong. And the transformation that we are using is we're replacing that designated symbol name by a new symbol none. All right, so we get, after applying that patch, the rule on the right-hand side. We also use the same notation to actually describe that patch. In order to reduce the search space, we're going to look at lexical information around the parse error locations to see whether these patches are actually usable. So we're going to look at all failing test cases in which the underlying rule from that item has been applied, and we look at the lexical context around the error location. We're going to collect all the tokens that are occurring on the left-hand side of the designated position, basically the last tokens before the syntax error. We call these the good tokens because they have still been eaten up by the parser. And then we look at the bad tokens, those that actually triggered the syntax error. And we use the set of the good tokens and the bad tokens to describe whether a patch is applicable. All right? So we use this first to eliminate items, possible rules with locations, that cannot directly reflect the error location. And so we check whether anything that could have been used on the as token or could have occurred as token on the left-hand side of the designated position is in the set of good tokens. That means that the rule actually came through or that the error location was actually achieved through this rule. So any rule that doesn't satisfy this condition or a weaker form of this gets thrown out. It cannot be a repair because it didn't go through the context in which the error occurred. Similarly, we use this information to throw out candidate edits that cannot improve the grammar. And the idea here is that we only allow such substitutions such that the right of the patched rule eats up up at least one of the bad tokens. Right? If the change to our rule doesn't allow us to actually eat up at least one more input symbol in at least one test case, then it can't fix the grammar. That's our basic assumption. So we can use this to rule out possible edits that cannot improve the grammar. In this case, replacing name by none satisfies this, but it's not the only one. There is a number of possible substitutions that could be used, right? In effect, anything that contains num in its first set can be used to replace name. So this is using or exploiting the information from our test cases, but we can, the lexical information around the parse errors, but we can exploit more information. We can actually use more information from the parsing tests in our test suite to restrict patches even further. So we're going to look at all pairs of tokens, all bigrams that are legal in the test suite. All right, so if we have our test suite on the left-hand side, we can extract the list of pairs that are legal in the target language that we don't know. And we can exploit this to eliminate patches afterwards, basically as a post condition on the patch. Right, so we check for a substitution, for instance, we check that anything that can occur on the left-hand side of the designated position after we've patched the rule, and anything that can occur on the right-hand side of that patched symbol, that these pairs of tokens have actually occurred in one of the examples, right? So that they're one visible, viable bigram. We also check that the same property holds one token to the right. So now we're checking not directly to the left of the designated position, but also to the right of the designated position. And so we can formulate these kinds of patch validation rules for each kind of string edit operation. So in this case, all of the patches are, or the patch is validated because the conditions hold. So that means we can apply this transformation, changing name into num, with the hope of improving the grammar. Let's look at a second example. Let's look at the deletion. All right, so our test suite still fails even with that patch because it expects not a closing bracket at that position. All right. So we look back at our grammar, we see that there may be something wrong with the name rule, something else with the name rule, namely that it doesn't allow an empty argument list. Right? So we can try to fix this by deleting name. Name list goes to empty, so that would allow this, right? So we patch this by deleting one symbol. We go about as before. We collect the lexical information around the parse error. We check that the left set is contained in the good tokens. So the rule, the error is achieved through that rule. We check that the candidate grammar improves the actual, or that the candidate edit improves the grammar. Right, so we check for a deletion that the right set is actually eating up one of the bad tokens, which is the case. And then we do our patch validation. And in this case, that works as well. Now the patch validation on the pairs actually doesn't work because one of the legal patches or legal pairs that can be derived using the patch grammar contains the token sequence open bracket comma, which is not valid, which is not observed in our specification. So we rule out this patch. We can fix this actually by removing both name and name list, right? So in that case, everything works out as expected. Right. There's more examples and there are more details in the paper. We have about half a dozen different patch operations with the corresponding conditions. So where does this make sense? Our assumption is that this is useful whenever we have a reasonable initial grammar and driving examples. Basically, if we have a competent grammar developer who got it almost right, but not completely wrong. Right? So one example where this is usable is, for instance, in teaching. We've built a feedback system that automatically provides hints to students. We can build these repairs into the system to provide additional hints, basically automating student assistance in the process of grammar development. We can use this for grammar recovery and maintenance. There's a lot of work in trying to map different sub-grammar or subversions of languages onto each other. We can also use this in genetic grammar learning, where we try to infer a context-free grammar from examples. We'll be focusing on the first two examples here. And so the first thing we did is we tried to fix student grammars. Now, these are grammars that students have submitted for a compiler engineering course. These are the grammars that contain errors, but trust me, and if you've taught compilers yourself, you know that students actually make a lot of mistakes in formulating grammars, even if they have descriptions and examples. These languages here are not super large. They're like medium-sized Pascal-ish languages. The number of rules is about, what do we have? 70 to 100 rules. That's the number of rules that the students have written. We have a couple of bugs in these, relatively few bugs in the grammars, 1, 2, 3. In some cases, in the last case, we don't know how many bugs were there because we're not able to repair it even manually. A few failing tests, right? So these are almost correct grammars. The students pretty much got it right, but a few corner cases, they got it wrong. And we can use our tool now to fix these automatically. Mostly, we find fixes. Mostly, we find them relatively quickly. It takes between a minute and 20 minutes. One example, we failed to find a fix. That grammar was just broken beyond repair. And on the right-hand side, you see what different patches have been used. The patches that we found are, we like to claim, of high quality. So everything that has a star patches default in the grammar to human quality. In some of the cases, we actually do the patch that a human would be doing. A check mark means that it passes all tests, but it's a limited quality fix. And one, as I said, failed completely. We can handle grammars with multiple faults, which is good because students do make multiple faults. Let's look at two examples. Number 2 is a small grammar where there is a single fault in there with, I think, 3 failing tests, right? Here is an example of failing tests. I don't know whether you can see it. There's a comma after the second A in each program. So there's a variable list with 3 A declarations, or 2 separated by a comma, and the parser that the student wrote fails to accept these valid test cases. Right? If you look at the grammar, we can see where the fault is. Can you see it? Can you spot it? Right? The rules variable IDs is wrong. Right? It starts with an identifier and then a comma, but it can go to empty, which means that it always assumes an identifier, but it should be applied in a context where it should first see a comma. Right? So our gfixr system fixes this immediately. That goes very nicely. Here's a second example that had 4 errors in there and a larger number of failing test cases. Here are some of the failing test cases. So the errors are: the student grammar doesn't allow bracketed expressions. It doesn't allow sequences of strings, the strings separated by the full stop, to be printed. And it doesn't allow function calls without arguments. Right? So here is the student grammar. You can see what goes wrong. The factor doesn't have a rule for bracketed expressions, and the function call rule id alpha comma expert doesn't allow an empty list comma expert. And you can see that the write function only allows up to 2 arguments. So we fixed this, I think, with 7 iterations, with 7 patches and about 300 candidate grammars. It takes a while, about 25 minutes. All right, so we fixed the expression part completely. We insert a rule for bracketed expressions by duplicating the not factor rule and replacing the not by an open bracket, and then inserting the closing bracket. We also fixed the function call rule simply by deleting the comma expression occurrence in the right-hand side, right? And we kind of fixed the print rule by adding a rule that allows 3 strings to be printed, which is all that our examples give us. All right, so it's a bit of an overfit in parts, but in other parts, it's an actual real human level fix. It's not too bad, in my opinion, but I may be biased, of course. There are more examples in the paper, or in Moketsi's thesis, if you're interested. A second example, we looked at larger grammars. We looked at Pascal grammars that were written in Antler and Cup. These were supposed to actually describe the same language, but they don't. If you look at the type subgrammar, you can see that the Antler rules are more comprehensive than the Cup rules. Right? So Antler's version allows function and procedure types. The Cup rules don't allow that. And so how do we fix this? We're going to take the Antler grammar as specification and generate test cases from that. And then we repair the Cup grammar against that specification. Right? So here's the test cases that we generate, and we eventually get a version of the Cup grammar that accepts the same type language as the Antler grammar. So this would be a way of automatically merging 2 versions of purportedly the same language into one. Right. So in conclusion, we've described the first approach to automatically repair bugs in context-free grammars. The 2 or 3 main ingredients that make it work is that we use an improved version of spectrum-based fault localization to pinpoint suitable fault locations, and that we use a series of small-scale transformations with explicit pre- and post-conditions as patches. We've implemented this and used it to actually repair student grammars. In fact, Moketsi was my TA for compilers last year as well, and so all of the feedback was auto-generated. All of the repairs were automatically generated by his tool. This is a 2021 paper. We were looking at several items or directions for future work. The one that we've actually ended up doing is active repair. So far we've assumed a fixed library of tests against which we fix. We changed this to generate tests as we go from each of the candidates that we produce. The advantage of this is that it reduces the dependence on the given test suite. In fact, you do not need an initial test suite at all. You can start with a candidate and generate tests from that. What you do need, though, in order to make this work, is you need an implementation of a parser for the target language as Oracle that can tell you whether one of these generated tests is actually in the language or not. Right. I was going to show you something about this. I'm going to ignore all of this. All I'm going to show you is a huge symmetry of numbers, because I want to show you something that we learned from this, right? So the active repair is on the right-hand side. The passive repair, which I've described before, is on the left-hand side. the active repair finds more bugs in the grammars because it generates other test cases that weren't there when we started. In fact, it generates about twice as many test cases as we originally had. So it's not a huge effort. It takes twice as long to find the actual patch because we need more iterations, because we have more bugs to fix. In return, we get many perfect repairs, basically 100% precision and 100% recall defined on generating tests from the candidate grammar and from the article grammar. In general, we get a higher F1 score in most cases. There are a few cases where the active repair actually loses out. So this is nice. This is probably the first time I've ever given a talk where I could refer back to the future work and have done it. Thank you. If there are any questions, I'm happy to take them.
Thank you for the nice talk. I have a few questions about, well, in the, so you're looking at some oracle at the end, and you also mentioned that maybe you have some examples of certain things like to parse. And where do you envision that these come from in practice? Like if someone is designing a new language, they would provide those input examples that they like to parse, and
yes.
Okay, interesting.
So it depends a bit on the scenario, right? In the teaching scenario, the teacher has presumably the golden grammar, right? You write your grammar for your parser before you give the assignment to the students. Well, I don't often do this, but in principle, you should be doing it. So you can use that golden but hidden grammar to generate the test cases. Pick a few of these to give them as illustration to the students and use that test suite for the repair. If this is more like a production environment, you would assume that people who develop the grammar, write down a few examples. Is this what we want? How does it look in practice? So we're assuming that there is at least a relatively complete set of tests available. It should at least cover all rules of the target grammar, right? You can't repair if you don't have an example for that.
Right. Okay, that makes sense. And I assume that there's multiple ways to prepare the grammar to meet those ways. Do you have some metrics that prioritize which repairs to choose in the
Yes, we do. So actually, the underlying algorithm keeps all candidates in a priority queue, and we use the number of passing tests and the length of the fragments that have been successfully parsed, and several other things as sort of key into that priority queue, so that the grammars that are at the top of the priority queue are actually the best candidates so far. So we basically measure the fraction of successfully parsed examples and use that to index into the queue.
Okay, interesting. And finally, you mentioned that you do some analysis of the lexical environment around this. And it wasn't clear to me how this is mapped back into the surrounding grammar, and would it be easier if you had a grammar and a lexer that was combined into one, or do you see these as separate things?
So we've done this with CUP because it's easier if you have a separate lexer. The repair is easier. Fixing lexical tokens is hard work because of that separation. But what we're doing here is we're just basically looking at the error output and then analyze the location and say, okay, this is the last token that has been successfully consumed, and this is the token that has triggered the actual error. And then we use these pairs or these sets of good tokens and bad tokens to see whether the error could have been achieved by using that rule. So basically, the designated position, the bullet, needs to have a good token on the left-hand side and a bad token on the right-hand side. If that's not the case, then that rule can't have been used to generate that error.
Thank you.
That's another question. Well, go ahead.
Thank you for the really nice talk. This was really interesting. I have a few questions. So there was this old research on error correcting grammars, error correcting parsers from 1970s.
Yes.
Where, it's on the other side. It's about correcting inputs or grammars. But many of the operations that you use, like deletion, insertion, these minimum distance deletions and other things, inside the algorithm, you can always switch it between correcting the input and correcting the grammar itself. So how do you, can you actually tell me a little bit about why the other things are necessary rather than simply fixing the error correcting parsers implementation itself?
So you may want to use that grammar for other examples, right? So, I mean, the main reason these days to have a grammar is not to write a compiler, but to use it for fuzzing. Right? So fixing the error correction in your parser isn't going to help you with fuzzing.
So the error correcting parsers, what they typically do is that they find the smallest set of tokens that are different between the grammar and the input. And at that point, they change the input. But there, you could also have changed the grammar instead.
If you look at the deletion rule, what this is actually a grammar level fix of penning mode synchronization from error correcting parsers. The underlying ideas are very similar. We just flip them around and use them in a different way. We made this a separate thing because it's just easier to modify an explicit grammar rather than going through a convoluted parser implementation with all of these error repairs that are in there. But the underlying ideas are so like mirrors of each other. I agree. And I think we say it even in the paper that this is panic mode's recovery.
Okay, thank you for the question. Thank you for the talk. And surprisingly, the next talk is also by Fischer. Now, and also by Patsy Zero, and with co-authors Philipp van Herden and Kostas Zagonas. And now it's grammar-based testing for little languages and experience report with student compilers.
Right, so this is a paper from SLE 2020. This is again work of Moketsi and Philipp van Heerden, who was an MSc student, and Kostas Zagonas from Uppsala, who's worked on property-based testing. And so if you want to leave now, the idea here is property-based testing in grammars to test compilers. You can go back to sleep. Right. Here's the big question in testing compilers. Can we actually generate test suites that are as good as manually crafted test suites? Building a test suite for a compiler is hard work. So can we get around this hard work by generating it automatically? And that's the question we are trying to answer experimentally in this paper. The first thing to know is, what does it mean as good as manually crafted? Right, so there's 3 dimensions to this. The first one is it reveals as many faults in the underlying compiler as the manually crafted one. Right? Crashes or false positives or false negatives or miscompilation. Compiler crashes you really don't want to see. The second one is perhaps you want to look at the coverage of the system under test. So does the test suite that you automatically generate induce the same code coverage as the manually constructed one, statement coverage or branch coverage? Or does it induce the same coverage on generated error messages? So those are 2 dimensions. The third one is we want actually a precise oracle. If we manually craft a test case, we know whether it's supposed to be passing or failing, whether there's a syntax error or a semantic error in there, and what kind of semantic error there is. And what's the point of generating tests where we don't know the output? That is only crash testing. So we need to know at the syntactic level whether the test case is assumed to pass, i.e. the parser accepts the input, or whether it's assumed to fail. And if it fails, it would be really nice to know the error location to make sure that the parser fails the right way. At the semantic level, we want to know what the expected error message is, undefined identifier, or repeated declaration, or type mismatch. So the first two things and the syntactic oracle are relatively easy to achieve, but the semantic oracle is hard. As I said, this paper provides an experimental answer to this, well, at least for small languages. So the language you've just seen in the previous example is actually one of the languages we're using here. I doubt that we will be able to generate test suites anytime soon that are gonna test the latest version of GCC or Clang or MySQL. Although for MySQL, it's probably doable. Right, so it's an experimental paper. We started with a small language called EMPL, or a modest programming language. On the left-hand side, you see the full grammar. So it's about 50 different non-terminal symbols, even fewer, about 90 rules, the same size as we've seen in the previous talk. On the right-hand side, you see the errors that are expected. In fact, this is a language that's been used, let me go one slide forward and go back. This has been a language that's been used by one of my colleagues in Stellenbosch in a second year computer architecture course where the students were given a 60-page documentation describing the language and the target environment, and were asked to write in C a single pass recursive descent compiler that compiles from this EMPL notation into Jasmine bytecode. And the colleague has used a very strict framework for the implementation and evaluation and the marking. Right. The high-level architecture was given, the error handler was given, the build script, the test harness, all of this was given, which makes the evaluation a lot easier, right? And as part of this, the document specified which errors the grammar or the compilers need to find. There's a couple of syntax errors, there's a couple of scope errors, the usual thing you would expect, repeated definition or use of an undefined identifier. And then there are a couple of type errors. You use an identifier in a function called position, and it's not a function, or it's not a procedure. Or you have a type mismatch in an assignment, or in any of these other syntactic categories. So it turns out there are actually exactly 26 prescribed errors, which makes life nice. We took the student submissions that were submitted by this course. There were 94 students enrolled in that course. 33 of those students submitted for marks a version that just doesn't even compile. Just to give you some indication about student quality if you don't have that. 61 of these submissions actually compile, build, and execute. The average code size of these things is about 1,300 lines of code in C with a reasonably large variance. Some of them were pretty ugly monsters. We also got the test suite that the instructor used for marking. That contained 48 tests with syntactic errors, 79 syntactically correct programs with semantic errors, and 103 correct test cases. These were unseen by the students, but they were designed by the instructor to flush out errors. So our working assumption is that this is a reasonably good test suite. In fact, the instructor has been using this setup for 10 years running and modified the languages over the years and build up the test suite over the years. So this is representing a substantial engineering effort in building a test suite. So first experiment, can we check the syntax of these programs? Or more precisely, can we check whether the students build parsers that follow the syntax? So what we need is a syntactic oracle. We need to know whether the test cases must be accepted by the parser or whether they must fail. The purpose here is mostly crash testing. And we're using an oracle by construction, which means we use a test suite algorithm, a test suite construction algorithm that produces tests that are guaranteed to be positive or negative. All right. So these algorithms are typically based on derivations. The grandfather of all of these algorithms is Purdam's algorithm that generates a test suite that uses each rule in the grammar at least once. But Purdam's algorithm tries to minimize the test suite. So it produces the minimum number of tests that cover all rules, which is a bad idea if you try to test compilers, because the tests are too complex. There is a different class of algorithms that kind of minimizes the individual tests, basically isolate the rules as far as possible. They all follow pretty much the same thing. Now, we had a data log talk in the morning. I am a Prolog guy. This is the high-level idea. This is, in fact, the Prolog implementation of the test suite generator. We iterate over all symbols. We find a minimal embedding of the symbol from the start symbol. We expand the criteria at the symbol, and then we complete this into a full derivation so that we get an actual word in the language. And the variance is the different criteria. For instance, in order to produce a test suite that guarantees that each rule is used at least once, we just need to pass rule as argument into this generic algorithm. CDRC is a more complex version that uses each rule on each occurrence of the left-hand side of that rule as on the right-hand side of another rule. Read up on this. This is a paper by Ralph Lemmer about 10 years ago. So there's a number of these different coverage criteria that have been widely used. Mostly, we had this discussion, mostly for fuzzing purposes. We've also used plain old random derivation, brute force, and bloody ignorance. It works surprisingly well, as we will see. We've also looked at a variation of the generic cover algorithm that mutates the rules, going back to a paper we've presented at SLE 2019, to generate tests that have guaranteed syntactic errors in them. Right. So, what does it teach us? What did we learn? The first thing that we learned is the obvious thing. If you generate longer derivations, more complex tests, then you get a better coverage of the system under test. Right? But it doesn't work that well. So here we see the three different criteria: rule coverage, CDRC coverage, 3-level step coverage, 4-level step coverage, and so on. We see that they're basically the same construction. It's just the length of the chain that gets longer and longer. In rule coverage, we have a 1-step chain. In CDRC, we have a 2-step chain. In step 3, we have a 3-step chain. So these produce basically more and more complex test cases where rules are used in more and more complex contexts. And it's obvious that this leads to a better coverage of the system under test, but it really, really doesn't help. Right? So the series of box plots shows that the median coverage over the systems is around 65 to perhaps 70%. The box plot, the upper line of the box plot is 75 percentile, the lowest 25. So in 25% of the cases, the test suite induces a coverage of 70 to 75% or more. The circles at the top are the outliers, so in none of the compilers, we get a coverage of more than 80%, which isn't great. And it's even worse if you compare this to the manual test. We just look at the syntactically correct test cases from the instructor. Basically, the 23rd percentile, third quartile of the instructor test suite sits above the first quartile of the best syntactically generated test. So in terms of covering the system under test, generating systematic test suites is not very useful. In terms of breaking the systems, it is slightly better. Right? We see that with longer and longer derivations, we get more and more compilers to reject legal inputs or to even crash. But even there, we trail behind the instructor's test suite. So remember, we had 61 benchmarks that we're building. On the instructor's test suite, only 6 of those 61 pass all syntactic tests. 95% of all students were unable to write a simple recursive descent parser that follows a given EBNF. They were basically unable to translate from LaTeX into C, which is frightening, and I hope it's not an indictment on the quality of our students. Now, Mokatsi was one of our students, so it's not an indictment. Right. So that is not a good thing. Right. So what about brute force and bloody ignorance using random test suites? Now here the picture becomes more interesting. We learned that random test suites outperform systematically constructed test suites of the same size, but they're still behind the manual test suite. So if you want to generate tests, don't bother with anything smart, just random generate tests. Now, there is a huge, and I can't underemphasize how big bias risk there is. It depends on how you select your roles, how you apply your roles, how you construct your tokens, how do you enforce termination, what the test size and the test suite size are, and all of these things. So our results, strictly speaking, only hold for random construction using a K-level rule-weighted breadth-first expansion using minimum yield completion with random token duplicate preservation and a fixed test suite token budget. Those are 8 different dimensions, I think, that induce a risk. Read up in the paper what the alternatives are. But what we see is that bang for the buck, random does pretty much better than systematic, right? So rule and step 4 are systematically generated test cases. 5K is a 5,000 token overall test suite, randomly generated, which is the size of step 4. So there it's slightly better. But if we go further, if we spend more effort, we get better than systematic. So random test suites outperform systematic test suites. They perform roughly the same at the same size, but when they get bigger, they outperform. We see that the number of failures goes up, but it's slightly lower than the instructor. Well, it's lower than before, and it's lower than the instructor one. But the number of crashes is very high. And with large random test suites, we pretty much get to crash every single student component. The real win comes in from combining random test suites and systematically constructed test suites that also contain negative tests. So this is the bar SYN plus 500K. That's a large random test suite and a variation of deeply nested syntactically constructed tests. It outperforms the instructor's test suite. In fact, we managed to break every single student submission with that thing. Right. Now, I've talked too long about syntactic stuff. Let's quickly touch upon, can we do this also for semantic tests? Can we go beyond crash testing? Right? So can we generate tests that break the semantic rules of the language? Right? So we'll focus on scoping and typing rules, basically on a symbol table. And so we're going to use a semantic test suite construction algorithm that is based on a property-based generating test algorithm. The idea is that we add a semantic markup to the grammar rules. Right? So this underscore decal that's tagged onto the ID says this is a declarator position for the identifier. It needs to be inserted into the current scope of the symbol table. So this is now a modified context-free grammar, just using different terminal and non-terminal terminal symbols. We use that grammar to random generate skeletons that still contain this markup. And then we run a rendering engine over this that interprets this markup and produces the actual tokens, the identifiers. And skeletons that cannot be rendered completely because they describe an illegal input just get thrown away. So the rendering engine just contains a small symbol table implementation. All right. So this is a very lightweight approach. Here you see the full markup that is required for that language. We need to mark up 7 out of the 45 rules in a few positions. Basically, we need to say when a scope is entered and left, and whether a variable occurrence is a declaration or usage, declare or reference. Right? So the declare basically in the rendering engine inserts a fresh name into the current scope. The construction of the context-free structure of the skeletons that we're generating guarantees that the scopes are well found. And we can then use, so like a mapping that has callbacks into our rendering engine to interpret what the rules mean, right? So ID decal means insert something in the current scope, declare an identifier, a fresh identifier in the current scope. Ref means look up in all scopes that are visible right now. Right? So these things on the right-hand side of the squiggle rows are basically callbacks into the rendering engine, and they return a string for the identifier to be printed. It's basically like LaTeX or HTML. We can use this to break the rules. We can inject specific errors into the programs by overwriting these mediator mappings. We can, for instance, force a repeated declaration by overwriting the declare thing to produce a name that's already in scope. So we basically have our skeleton here, and we want to generate one that has 2 repeated declarations, and we achieve this by overwriting the rendering of the decal to return a name that is visible in the current scope. Actually, that is declared in the current scope. Not visible. Right? We can use this also to check that the compiler deals with shadowing correctly by returning a name that is visible but not declared in the current scope. We can generate a test that produces a reference to an undeclared identifier by basically overwriting the reference markup to return a fresh name in the current scope. Yeah. Let me skip over the typing stuff and just let me show you some examples. So this was actually quite neat. In this case, the instructor had not only the grammar, but a golden implementation of the entire compiler. And we broke that thing. So here is an input that the compiler of the instructor accepts, and it generates actual class file for this. But there's an error in there. Can you spot that error? This is like a standard Pascal-like language. There's a typing
error in B1A?
Yes. All right. So B1A is an integer array variable, and it's being assigned a function that returns an integer array. All right. But that is a function instead of a verb. So the instructor's compiler eats this up and produces a class file that then duly crashes over. But we can generate a test case, and this is not even a reduced test case, can generate a test case that fixes it, that finds this. Here's another example. Here is where the instructor produces an error, but it's a legal program. Right? The instructor's implementation complains about incompatible types. It even tells you that an integer array and Boolean at the third parameter of the function n are not compatible. But if you look at this, it is actually true, right? I mean, GS81 is an integer array. It's declared as an integer array that matches the type that's required. So the instructor was hand waving. I think there's an off by one error somewhere hidden there. Again, more examples, more results, more details are in the paper. Right. To conclude, we've experimentally evaluated existing grammar-based test suite construction methods. We've shown that at least for small one-pass compilers, the test suites based on systematic coverage criteria are worse. They cover less code and find fewer errors than a manual test suite. Random test suites are better, and the combination of random and systematic test suites are performing on par or better than a carefully manually constructed test suite. We've introduced a lightweight extension that allows us to guarantee semantic properties. It's based on markup tokens that are added to the rules, and the evaluation is promising. We broke the golden implementation in at least 2 cases. Now, this is one of the papers where the future work, of course, hasn't been done. It would be nice to apply this to larger and complex languages. And at some point, Amazon was promising me money to do this for Rust, but then they said, no, sorry. So if somebody has €500,000, I'll build you a Rust compiler checker. Actually, I'll do it for 50,000. Very cheap. That's all. Thank you.
Questions?
Very nice presentation. So I have a couple of questions. First, there are a lot of papers, a lot of literature in compiler testing. So are the results similar to what they have done, or what are their insights from all those compiler testing papers?
I'm not aware of any papers that have actually done an experimental larger scale evaluation and explicitly compared systematic test case generation to manually constructed test suites. So if you know any papers that we are missing, I'm really happy to learn about those.
Yeah, I mean, most of the compiler testing papers, in their evaluation, they evaluate like a corpus generated by their tool to the test suites of the compiler.
None, I mean, as I said, I'm happy if you have any specific references, please find me right after the talk.
I can give you another reference.
Okay.
And another one is about the cases so that if you generate larger test cases, it's more probable to find the bug, but you don't increase the test coverage. And here you mentioned test case reduction. So did you actually try that to reduce the large test cases?
I mean, basically, something like delta debugging could be used. So if you generate a large test case like a large random derivation, you don't quite know where the fault is. So the idea would be to use something like delta debugging.
Yeah, I mean, C reducer works pretty well for test cases, for compiler testing. So maybe you can try that.
Yeah, you can use something. I mean, C reduce is basically, as far as I understand it, an implementation of delta debugging on top of CSmith.
Not exact, but yeah.
So yes, this is not a major aspect of the work. It would be nice to have to make it more usable. I'm in full agreement. It should be done, and I don't think it's a difficult thing.
Cool. Thank you.
Yeah, I have a question.
Sure.
Obviously, it's more difficult to find examples of programs where all the semantic conditions are fulfilled. What kind of specification would you need to do that? Yeah, I know that there is work to like generate type correct programs, for example. Then you also need something to generate entity type incorrect programs. Yeah, and then there are other semantic errors that you might also want to do.
So what this implementation is doing, the rendering engine basically takes care of the semantics, and the rendering engine just contains a simple generic symbol table that you select parameterize or customize through these callback functions. Now, I think, well, that's scope and type rules, at least for a simple type system. Something like ownership types would be more complex. Anything that goes towards program verification, I don't know, termination or something like that, or array out of bounds, too hard. I don't think this is within scope of this work anytime soon. So we've basically looked at what can we do and build our system around our assumption what's feasible.
I was kind of wondering what do you think, what kind of specification would be needed?
I mean, you can see this actually as a specification, right? So here's the specification. It says when you declare you're entering a scope, you're basically adding a new transparent boundary level to your symbol table. So you can look up but not down. So you can see this as a very small domain-specific specification language for symbol tables. You could try to use generic attributed grammars. I try to stay away from these because you always end up with some kind of Turing completeness. So I don't know. If you have ideas, I'm happy to talk. That's one question.
If I can quickly follow up on that. With Comic, how many errors have you found in your rendering?
We haven't eaten our own dog food. No. So
it's crucially dependent on that rendering actually doing something.
Yes.
I wonder about the theoretical background for what the rendering engine does. Did you use attributes or?
No, this is a product program, right? So these are basically product predicates that are called when we go over the skeleton and pretty print it, or actually ugly printed into ASCII. So it's very simplistic, and yes, it's correct by construction. Now, I wouldn't trust it too far. But I don't think that it invalidates the conceptual approach, and it certainly doesn't invalidate the experimental results, because all of the faults that we found are real faults.
Okay, then let's thank the speaker.